Fundamental forces in nature. We all have an intuitive notion of force. In our experience, force is needed to push, carry, or throw objects, deform, or break them. We also experience the impact of forces on us, like when a moving object hits us or we are in a merry-go-round. Going from this intuitive notion to the proper scientific concept of force is not a trivial matter. Earlier, thinkers like Aristotle had wrong ideas about it. The correct notion of force was arrived at by Isaac Newton in his famous laws of motion. He also gave an explicit form for the force of gravitational attraction between two bodies. We shall learn these matters in subsequent chapters. In the macroscopic world, besides the gravitational force, we encounter several kinds of forces: muscular force, contact force between bodies, friction, which is also a contact force parallel to the surface of contact, the forces exerted by compressed or elongated springs and taut strings and ropes, that is tension, the force of buoyancy and viscous force when solids are in contact with fluids, the force due to pressure of a fluid, the force due to surface tension of a liquid, and so on. There are also forces involving charged and magnetic bodies. In the microscopic domain, again, we have electric and magnetic forces, nuclear forces involving protons and neutrons, interatomic and intermolecular forces, etc. We shall get familiar with some of these forces in later part of this course. A great insight of 20th century physics is that these different forces occurring in different contexts actually arise from only a small number of fundamental forces in nature. For example, the elastic spring force arises due to the net attraction or repulsion between the neighboring atoms of the spring when the spring is elongated or compressed. This net attraction or repulsion can be traced to the unbalanced sum of electric forces between the charged constituents of the atoms. In principle, this means the laws of derived forces such as spring force, friction are not independent of the laws of fundamental forces in nature. The origin of these derived forces is, however, very complex. At the present stage of our understanding, we know of four fundamental forces in nature, which are described in brief here. Gravitational force. The gravitational force is the force of mutual attraction between any two objects by virtue of their masses. It is a universal force. Every object experiences this force due to every other object in the universe. All objects on the earth, for example, experience the force of gravity due to the earth. In particular, gravity governs the motion of moon and artificial satellites around the earth, motion of the earth and planets around the sun, and of course, the motion of bodies falling on to the earth. It plays a key role in the large-scale phenomena of the universe, such as formation and evolution of stars, galaxies, and galactic clusters. Electromagnetic force. Electromagnetic force is the force between charged particles. In the simpler case, when charges are at rest, the force is given by Coulomb's law, attractive for unlike charges and repulsive for like charges. Charges in motion produce magnetic effects, and a magnetic field gives rise to force on a moving charge. Electric and magnetic effects are in general inseparable, hence the name electromagnetic force. Like the gravitational force, electromagnetic force acts over a large distance and does not need any intervening medium. It is enormously strong compared to gravity. The electric force between two protons, for example, is 10 power 36 times the gravitational force between them for any fixed distance. Matter, as we know, consists of elementary charge constituents like electrons and protons. Since the electromagnetic force is so much stronger than the gravitational force, it dominates all phenomena at atomic and molecular scales. The other two forces, as we shall see, operate only at nuclear scales. Thus, it is mainly the electromagnetic force that governs the structure of atoms and molecules, the dynamics of chemical reactions, and the mechanical, thermal, and other properties of materials. It underlies the macroscopic forces like tension, friction, normal force, spring force, etc. Gravity is always attractive, while electromagnetic force can be attractive or repulsive. Another way of putting it is that mass comes only in one variety. There is no negative mass, but charge comes in two varieties, positive and negative. That is what makes all the difference. Matter is mostly electrically neutral, that is net charge is zero. Thus electric force is largely zero and gravitational force dominate terrestrial phenomena. Electric force manifests itself in atmosphere where the atoms are ionized and that leads to lightning. If we reflect a little, the enormous strength of the electromagnetic force compared to gravity is evident in our daily life. When we hold a book in our hand, we are balancing the gravitational force on the book due to the huge mass of the earth by the normal force provided by our hands. The latter is nothing but the net electromagnetic force between the charged constituents of our hand and the book at the surface in contact. If electromagnetic force were not intrinsically so much stronger than gravity, the hand of the strongest man would crumble under the weight of the feather. Indeed, to be consistent in the circumstance, we ourselves would crumble under our own weight. Strong nuclear force. The strong nuclear force binds protons and neutrons in a nucleus. It is evident that without some attractive force, a nucleus will be unstable due to the electric repulsion between its protons. This attractive force cannot be gravitational since force of gravity is negligible compared to electric force. A new basic force must therefore be invoked. The strong nuclear force is the strongest of all fundamental forces, about 100 times the electromagnetic force in strength. It is charge independent and acts equally between a proton and a proton, a neutron and a neutron, and a proton and a neutron. Its range is however extreme small, of about nuclear dimension, that is 10 power minus 15 meter. It is responsible for the stability of nuclei. The electron, it must be noted, does not experience this force. Recent developments have, however, indicated that protons and neutrons are built out of still more elementary constituents called quarks. Weak nuclear force. The weak nuclear force appears only in certain nuclear processes, such as beta decay of a nucleus. In beta decay, the nucleus emits an electron and an uncharged particle called neutrino. The weak nuclear force is not as weak as the gravitational force, but much weaker than the strong nuclear and electromagnetic forces. The range of weak nuclear force is exceedingly small, of order of 10 power minus 16 meter. Towards unification of forces. We remarked in section 1.1 that unification is a basic quest in physics. Great advances in physics often amount to unification of different theories and domains. Newton unified terrestrial and celestial domains under a common law of gravitation. The experimental discoveries of Ørsted and Faraday showed that electric and magnetic phenomena are in general inseparable. Maxwell unified electromagnetism and optics with the discovery that light is an electromagnetic wave. Einstein attempted to unify gravity and electromagnetism but could not succeed in this venture. But this did not deter physicists from jealously pursuing the goal of unification of forces. Recent decades have seen much progress on this front. The electromagnetic and the weak nuclear force have now been unified and are seen as aspects of a single electro-weak force. What this unification actually means cannot be explained here. Attempts have been and are being made to unify the electro-weak and the strong force, and even to unify gravitational force with the rest of the fundamental forces. Many of these ideas are still speculative and inconclusive. Table 1.4 summarizes some of the milestones in the progress towards unification of forces in nature. Table 1.2 Link between technology and physics. Steam engine, laws of thermodynamics, nuclear reactor, control nuclear fission, radio and television, generation, propagation and detection of electromagnetic waves, computers, digital logic, lasers, light amplification by stimulated emission of radiation, production of ultra-high magnetic field, superconductivity, rocket propulsion, Newton's law of motion, electric generator, Faraday's laws of electromagnetic induction, hydroelectric power, conversion of gravitational potential energy into electrical energy, aeroplane, Bernoulli's principle in fluid dynamics, particle accelerators, motion of charged particle in electromagnetic field, sonar, reflecting of ultrasonic waves, optical fibers, total internal reflection of light, non-reflecting coatings, thin film optical interference, electron microscope, wave nature of electrons, photocell, photoelectric effect, fusion test reactor, tokamak, magnetic confinement of plasma, giant meter wave radio telescope GMRT, detection of cosmic radio waves, Bose-Einstein condensate, trapping and cooling of atoms by laser beams and magnetic fields. Table 1.3 Fundamental Forces of Nature. Gravitational force relative strength is 10 power minus 39. Infinite range operates among all objects in the universe. Weak nuclear force relative strength 10 power minus 13. Range very short subnuclear size approximately equal to 10 power minus 16 meter. Operates among some elementary particles, particularly electron and neutrino. Electromagnetic force relative strength 10 power minus 2. Range infinite. Operates among charged particles. Strong nuclear force relative strength 1. Range short nuclear size approximately equal to 10 power minus 15 meter. Operates among nucleons, heavier elementary particles. Table 1.4 Progress in unification of different forces or domains in nature. Isaac Newton 1687 unified celestial and terrestrial mechanics, showed that the same laws of motion and law of gravitation applied to both the domains. Hans Christian Ørsted and Michael Faraday in 1820 and 1830 respectively showed that electric and magnetic phenomena are inseparable aspects of a unified domain, that is electromagnetism. James Clerk Maxwell in 1873 unified electricity, magnetism and optics, showed that light is an electromagnetic wave. Sklidon, Glashow, Abdus Salam and Steven Weinberg in 1979 showed that the weak nuclear force and the electromagnetic force could be viewed as different aspects of a single electroweak force. Carlo Rubbia, Simon van der Meer in 1984 verified experimentally the predictions of the theory of electroweak force.